Okay, so I wanted to spend some time analyzing what we did in the last video, which was the guitar video. And so basically, if we have a guitar, something like this, have some strings, and we're going to say that that distance there is 0.647 meters. And if we look at the lowest string, ideally we want that to vibrate at 82.40 Hertz. So we want that to be the frequency. Okay, now one thing that I sort of put this diagram up before is the fundamental frequency of that string is going to be when it vibrates like this. So this is my 0.647 meters. That's the length of the string. But this is only 1/2 of the wavelength, because there's sort of an imaginary extension of that that makes the full wavelength. So the full wavelength is going to be up, then down. It's going to be one complete cycle. So I'm going to say that V equals lambda F, and I'm going to say that my V is going to be 2 times 0.647 meters, and my frequency is going to be 82.40 Hertz, and so that I'm going to get a velocity of 2 times 0.647 times 82.4. It's going to be 107 meters per second. Now the key thing here is that you have to remember this is just like what I did with the sort of the radio diagram, is that there's the waves are traveling at different speeds at different times. Okay? So the waves on the string are traveling at 107 meters per second. When those waves get transferred into the air, when they're transferred into the air, they're moving at 340 meters per second. So waves on the string, 107 meters per second. Waves in the air is going to be 340 meters per second. Okay, so now I want to look at this equation. V equals the square root of T over mu, and mu is the mass per length. Okay, so I look for a similar string. I measured that my mu for a similar string, not the exact same string, I said it was 10.89 grams, so I'm going to say 0.01089 kilograms per length. So my length was 94.8 meters, so 0.948 meters. So my mu was 0.01089 divided by 0.948. It gives me 0.0115 kilograms per meter is going to be my mu. Now I know my velocity, and I want to figure out what tension I should put the string under to get it to vibrate at that. So I want a vibrational speed, well, let's use the actual 106.6. So, well, let me rearrange that for a second. V squared is equal to T over mu. So T is equal to mu V squared. So my tension should be 0.0115 kilograms per meter squared. I'm sorry, that's not squared, the velocity is squared. And my velocity is going to be 107 meters per second squared. So using the exact values on my calculator, I'm going to get 106.6256 squared times my answer, and I get 130.6 newtons. So that should be the tension Now, if I look at a packet of, oh, there's no way you're going to be able to see this on YouTube. But if I look at a packet of strings, it says right down here that the tension for a 648 millimeter scale, blah, 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 the tension for that string should be 13.15 kilograms. So 13.15 kilograms. But of course, I'm working in newtons. So the way that we basically convert to newtons is we do our 9.81 meters per second squared for this case, and if I divide this by 9.81, I get 13.31 kilograms of tension. So tension should really be measured in newtons, but you know, I'm not going to call up the string manufacturer and complain. But basically, we get the right result, which is that our mu is that basically 11.5 grams per meter, and then that gives us, working backwards, we know what frequency we want, we know what our length scale is, that gives us a velocity of waves on the string, and that's going to give us a tension that we want in the string. Okay, I think I'm going to leave that there.